I'm getting a little window asking me whether I want to admit someone in the, from the waiting room. I assume
we will take care of it.
We'll take care of it. Yeah. I'm looking at that.
Okay, good.
You had to be made the co-host so that you could share your screen. That's the side effect of that.
All right.
Okay. Good morning, everyone, and welcome to today's ASSET Colloquium. And you have noticed already, obviously, that this is being held at a non-standard time. And again, seeing the speaker's name and affiliation, you should have also guessed the reason for it. Nevertheless, welcome all of you here. For just those of you, few of you probably, who would like to know what ASSET is about. ASSET is one of the three colloquia that happens, the weekly colloquia that happens at Tata Institute, that's TIFR. And this is in addition to the Natural Sciences Faculty Colloquium and also the Mathematics Colloquium, which happens on Wednesday and Thursday, respectively. So mainly the ASSET Colloquium deals with matters like this, which deals with technology, engineering, sometimes popular science, and also medical technology, and so on and so forth. So it's a great pleasure to today have Dr. Barry Bolting, who is the director for HPC GTM from AWS. And ASSET also would like to, of course, thank Girish, my colleague Girish Kulkarni, who's responsible for having this talk. And today Barry is going to talk on high performance computing in AWS cloud, innovating without infrastructure constraints. So without taking more of your time, let me welcome my colleague Girish, who will introduce today's speaker formally and also conduct rest of the proceedings. Over to Girish.
Yeah, great. Thanks, Satya. Thanks all for joining at this unusual time. We are very happy to have as our colloquium speaker today, Dr. Barry Bolting from Amazon, from AWS. He's going to talk to us about scientific high-performance computing on the AWS. As all of you know, the context behind this colloquium is that a lot of us have felt in TIFR that cloud-based scientific computing might have some unique advantages for us as a community because of its flexibility and other useful properties, right? But of course, there are also various concerns and questions that we always have. And so it was felt that it would be useful to have experts talk to us about cloud, tell us what's going on, and answer our questions. So today's colloquium is an attempt in that direction. Dr. Barry Bolting, our today's speaker, has over 25 years of experience in HPC. He's currently the WWGTM Director for High Performance, Autonomous, and Quantum Computing at AWS. But in his long career, he has fulfilled many technical and business roles at a number of leading computing companies, such as Cray, SGI, IBM, and so on. He was in an executive role at Cray for 10 years, where he actually developed on-prem HPC solutions. We have some Cray HPC at TIFR of a similar kind. Beyond Cray and all this HPC work, Dr. Bolting has scientific training as well. He has a statistical mechanics PhD from Stanford University. And so I suspect he's a uniquely suitable person to talk to us. He probably speaks our language as well as their language in terms of computing on the cloud. And I guess I'll probably end the introduction there. I'm really glad to, in particular, have Dr. Bolting speak to us from Seattle, where it's late Thursday evening. And so it's really kind of him to agree to speak to us. All I would say before handing over the call to him is let's hold on to our questions until the end of the talk. He has kept aside 15-20 minutes for Q&A. So we'll just let him speak and gather the questions later. And with that, Barry, I'll request you to start your presentation. Thank you.
Thank you very much, Dr. Kulkarni and Dr. Datar. I really appreciate being invited to speak to TIFR. It's a hallowed institution within the country of India and around the world, and it is an honor to be present here. Today, I want to give you a perspective on why I think cloud is a valuable infrastructure for approaching high-performance computing problems and can really benefit scientists and engineers around the world. One of the reasons I moved to AWS 2.5 years ago was because I saw that it could bring innovations to scientists and researchers in new and powerful ways. I'm a big believer in technology, and my years at Cray, being a technologist, taught me that the ways that I could help the scientific community was by providing them with tools. And those tools sometimes are in the form of equipment, infrastructure, sometimes it's in the form of expertise. And so one of the things I've done at AWS is build up a team that I think is equal to any team I have led at any of the supercomputing companies that I've worked for over the years. And the goal of that team is to work with scientists and engineers and help them to solve their problems on AWS. Today, I will give you an introduction. I think all of you know that high-performance computing impacts every aspect of our daily life, and none more timely than the work being done around the world to develop drugs and help with the global pandemic. We saw the innovation that it takes to develop vaccines in record time, and a lot of that work really takes place on high-performance computing infrastructures. And cloud provides the ability to bring those infrastructures to bear on scientific problems extremely rapidly. And you don't have to wait for someone to build your supercomputer and put it in place. You can actually, if you're faced with a problem, bring the infrastructure to the problem almost immediately. One of the fun things about AWS is that I get to work both with public sector and commercial companies around the world that are using high-performance computing. And I'll give you examples as we proceed through the talk of companies and institutions that are using our AWS supercomputing infrastructure to solve these types of problems, whether it's autonomous vehicles, seismic and reservoir processing and energy exploration, or whether it's financial services, studying whether what the risks are for financial portfolios, and also in the healthcare life sciences and in the basic sciences. One of the things that is extremely valuable about high performance computing in the cloud is that it can relieve the scientist from having to plan what their capacities, what their science is going to be using over the next 3 or 4 years, and allow them to evolve with their science. When customers need to purchase a supercomputer, an on-premise system, they have to evaluate and predict what their usage will be for several years. And then they have to take an average of all of the types of applications that they're going to be running and really find a arithmetic or geometric mean of performance that gives them the best average computational result, and then procure that system. I worked with NERSC, and Bill Kramer, the director of NERSC in Berkeley, published a whole paper on how you calculate the average best performance for applications and then purchase a system based on that. Cloud frees the researcher of this issue. They can now begin to think about each application and building up the infrastructure for every individual application. the choices that the researchers need to make then are in the area of what infrastructure, GPU, CPU, storage, best fits a given application. Let's take the example of WRF, a weather modeling simulation. You can look at the algorithms and decide that works best on an x86 architecture, and I need this much Lustre file system. You then can decide what scale you need to run the application, how many CPUs, how many compute nodes. You can then also look at the cloud portfolio and decide what type of pricing model do you want. Are you a commercial company that needs the result tomorrow, or are you a researcher that can wait till the following weekend, or get the results in a certain window of time? You can pay for the ability to get results much faster, or you can wait around and you can get something that is at a better price, but perhaps you get the results a little later. The agility to react. So if you're, if you have a medical situation like COVID, you can become agile. If you're a pharmaceutical company, you can begin to spin up resources and make those resources available to your researchers overnight. We had the situation when COVID first began that we were working with Johns Hopkins. Their models were not really built to scale to the level that they needed to have them scale in order to model all of the states in the United States and the countries around the world. And we worked with them and with FEMA to actually, over a 2-week period, give them a scale for their application that was 10 times more than they had when they started looking at modeling the COVID spread. And then they used this to predict how many hospital beds they might need. And this was very timely. We were able to bring this problem and scale it on AWS in a matter of days rather than a matter of months. As many of you know, when you buy supercomputers and you buy them, you look at several different basic components. And I'm going to talk about the basic components that AWS has. You look at the compute instances, the compute technologies. Do you want NVIDIA GPUs? Do you want ARM-based processors? Do you want x86-based processors? Are you experimenting with inference and training algorithms, and do you want special purpose devices? On the cloud, we offer all these options, and I'll go through a few of these in my talk. You also have choice of how fast the network is that you'll be running on. And this is really important for many MPI-based applications, such as computational fluid dynamics or weather and climate modeling, where you have the need for a tightly coupled set of resources with low latency and high bandwidth. You need data management. You need to decide, do you need large pools or data lakes with large data sets, such as a genomics data set, or a data set that comes off of a genomics device, such as an Illumina device that you're going to then do sequencing on? Or do you need a very fast Lustre file system that allows you to stream data into the compute or out of the compute? And finally, you need to make decisions about software and what types of orchestration and batch queuing do you have. When you purchase an on-premise system, you make many of these decisions once or twice, and then you configure the system and you live with that. And maybe that configuration is good, again, for the average application. But again, what if you could free yourself of that constraint and build the custom interface that gives you the best performance or the best price performance for every application that you run? The HPC stack on AWS is built of all of these components. And I won't go through this chart. We will provide you with the slides from today's presentation. But it does give you the idea that AWS provides a set of services that can meet every need of a scientific researcher, whether it's the visualization engines and access to data streaming and visualization streaming, especially remote streaming. Our NICE DCV product allows users to be on the other side of the world and be streaming data from their computations, or allows engineers and scientists sitting in 2 different countries to work on the same engineering problem. Cluster management and resource scheduling, compute, parallel file systems, object-based storage, high and low latency networks, high bandwidth, low latency networks, and durable storage for saving your data, for long periods of time. If you need to store that, especially if it's data that for governmental purposes, you might need to make available, we can provide worldwide backups of that data. One of the unique things we are beginning to do is pre-configure resources in the cloud. The first example of this that we've announced is the EC2 Ultra cluster, where we're able to spin up a set of A100 GPUs from NVIDIA. We call them the P4D family of instances, but these are basically, each one of these has 8 A100 GPUs. We can pre-configure that with Lustre file systems and with fast interconnect using our elastic fabric adapter. In essence, all of these GPUs are in a very tight area of our data center. So physically, they are close to one another, giving you low latency and high bandwidth. Many of the applications that this can be used for span large-scale distributed training algorithms, which are used for natural language processing, also for high-performance computing applications. So this type of infrastructure is the direction that we're heading, with making it very easy to spin up resources in the cloud for supercomputing. Now, I want to, yes, do you have a question?
Can I request you to switch your video off, if you don't mind?
Yes, I can do that. Is it a little choppy?
Yeah. Bandwidth challenge. Yeah, thank you.
Okay. Now I will talk a little bit about each of the technologies that we have, and then I'll go into the examples of the science areas that our customers are using AWS for. Core to our high-performance computing is our elastic fabric adapter. This is a special adapter that we put inside of each compute node or compute instance on AWS. And when we install this, it allows for an extremely low latency network access across different, between different compute nodes. Essentially, this allows for high performance computing applications that use lib fabrics. MPI is one of these. And so things like computational fluid dynamics, weather modeling, and large scale training are extremely effective with EFA. We want this to eventually be installed in most of the compute nodes that AWS makes available. Unlike some cloud providers, we do not build islands of InfiniBand within our infrastructure. What we want to build is a infrastructure across our entire backbone in our data centers that is high performance. And EFA is our own proprietary network adapter that allows us to do this. But because we build lib fabrics on it, we can use any standard MPI implementation on top of EFA. Lustre is the de facto standard high-performance file system for many supercomputing systems. And 2 years ago, AWS announced that we would be installing a Lustre-based file system in our data centers and allowing customers to spin up Lustre file systems when they needed them. The difference with an on-premise system is that you only need to spin up your Lustre file system when you need it and only need to pay for it when you're using it. What this does is it relieves the user of having to artificially construct very large Lustre file systems that they end up using for their home and standard storage. And that is not a cost-effective use of high-performance storage technologies. We can spin these up as either solid-state devices or hard disk-based devices, depending upon the performance and pricing requirements of the application. In terms of orchestration, I wanted to show two types of software that we make available. We have many, but these two types of software for job orchestration exhibit two of the options that are very common. AWS Batch is an elastic orchestration methodology that is cloud native, and it allows users to dynamically grow the compute instances, the compute families that they're using for a particular application, and grow them and shrink them in the middle of the application run. And this is very powerful. It's a different approach than setting up a fixed system and running a set of software within it. Instead, you use containers, in this case, Docker containers, to be able to elastically expand and contract the compute as the requirements are needed and provision these. Parallel cluster, on the other hand, allows you to deploy a fixed set of resources. So if I need 500 compute nodes, I can deploy 500 compute nodes, install Linux, install whatever software I think I need. This could be application software, it could be various MPI versions. There's no requirement for containerization, and I can deploy this much like I would deploy a supercomputer in my lab. And I can run my applications. I can run multiple applications within this cluster. It really is a cluster and mimics a cluster just like you would have on premise. I also wanted to discuss the various compute nodes that are common for high performance computing. AWS and many cloud providers have an alphabet soup of compute choices, and AWS is no different. It's almost a language in and of itself, but there are only a limited set of these compute nodes that are used commonly for high performance computing. And here I'm showing a few. It doesn't matter so much what the names are, but the way to think of it is that there are classes of compute instances that are large memory, where if you have large memory per core requirements, you would choose, for instance, the M family, M5, M5A, M5G. If you have a requirement for local solid state devices, you would choose another family. If you have a requirement for ARM-based devices, you would use the families that end in the letter G, which stands for Graviton. And Graviton is AWS's ARM-based technology. And then we have special purpose compute nodes. We also have NVIDIA nodes, and we have Intel-based nodes as well. But we also have a set of special purpose instances, such as Inf1, which is useful for inference for machine learning workloads. And we have F1, which is an FPGA-based instance based on Xilinx technology. All of these are at the user's disposal. All of these are at the scientist's disposal, and the scientists can choose the infrastructure that best meets their need. And finally, in August of last year, we released a set of compute services built around quantum computing. And this is an especially exciting area because as quantum computing technologies evolve, using quantum devices as an accelerator is going to become more and more prevalent. And today, with AWS Bracket, we are able to provide users with both true quantum hardware or with emulators so that they can do software development in a very cost-effective fashion and test out their quantum algorithms. This service is extremely exciting. We have a team of folks in India as well as in the US that are doing classes. Even as we speak, they're doing classes with scientists around the world and teaching them how to use the AWS Bracket quantum computing service. One thing that's really important for researchers is managing their costs. And I wanted to show an example. There is a partner that we work with, RONIN, based out of Australia, that has developed a set of software running on top of AWS that allows researchers to monitor their work, submit jobs very simply through a web-based interface, and monitor the cost of those jobs. So now they can deploy, and research advisors can see how much their research scientists are spending, can manage those projects, and maintain a budget for the researchers. This is extremely important in academics where many of the researchers are working on grants and using those grants and need to maintain their costs. So these types of partners are very important for AWS. And an example of a customer that's using RONIN is the University of Sydney. I wanted to put this example in because we're finding a lot of universities and national research laboratories are beginning to use RONIN as one of their solutions. It's especially suited to the academic environment. Now I want to go into applications and use cases and show you some of the results, because all of this has been fine words in the sense that they, I'm telling you we have an infrastructure, but I haven't shown you the proof. And I want to be able to show you the results of proper deployment of infrastructure for high performance computing. On AWS, as in any infrastructure, there are two key groups of applications that run for high performance computing. There are loosely coupled applications in which a researcher might run hundreds of thousands of simulations for statistical results, and those simulations are all independent. And the architectures that our customers use for doing distributed loosely coupled tasks can be quite different from the infrastructures that they deploy for tightly coupled MPI-based applications. So those are the two categories on which we tend to work with customers. As well, there are data differences, whether they're data light and don't need much high performance storage, or whether they're data heavy and need or require fast and high performance storage. So those are kind of the four corners of the design criteria on which our users begin to think as they use AWS in the cloud and design their infrastructure. And as you can see, many of you are familiar with these types of applications. Molecular dynamics there are some molecular dynamics applications that are heavily MPI based. or you can run many thousand small application sets with molecular dynamics and do statistics for ensemble averaging. So it can kind of land in both baskets. But things like computational fluid dynamics tend to almost always be run in a tightly coupled environment. And so examples of tightly coupled workloads are weather and climate. Maxar is a company that I'll talk about in a minute, doing computational weather modeling, production weather forecasting on AWS. Loosely coupled applications, an example is financial services risk analytics, where they're basically doing Monte Carlo simulations, thousands of those Monte Carlo simulations to mimic the risks, the financial risks in a portfolio. Companies like Schrodinger are using GPU-based accelerated computing to do docking, computer docking of drugs into protein and enzyme sites. Visualization, Autodesk and other companies are beginning to look at visualization and digital twins. AIML, the Formula One racing team, is using machine learning to try and optimize the data that's coming out of their cars and do computational fluid dynamics in a much more efficient way. A very exciting area, and hopefully this is coming through in the network, is the area of autonomous vehicles. And in the area of autonomous vehicles, AWS has a large number of customers we're working with. This is an example of a very complex workflow where the researcher has a large data set that comes from the LiDAR and visual components of the car, where they're collecting data from cars on the street. They take that data and they do machine learning training on the data sets. Then they take the newly trained models and they don't want to put them back in the car because they don't know that if the training has caused an anomaly and perhaps the car will be less safe. So what they do is they run millions of miles of car simulations and run those simulations much the way that you would run a video game. And they're simulating cars driving on the roadways. And that's how they test the newly trained data sets. And when they're satisfied through the simulations that the cars are safer than they were, or as safe as they were with the previously trained model, then they will deploy that model out into the vehicles. Another exciting area is in the area of genomics and imaging workloads. And we're working with a large number of researchers, both in the private and public sectors, to look at both genomics analysis and new technologies such as cryo-electron microscopy. And in, of course, many of these, it all begins with the production of large data sets, gigabytes to terabytes of raw data coming off of devices. Those are then cached, uploaded, cached, and refreshed automatically into the cloud using a wide range of possible conduits to get the data into the cloud, some directly over the internet, and sometimes through devices that are physically transported to AWS. And then they run simulations in the cloud and the scientists are able to collaborate with one another on the data and then report back on the results. One of the standard use cases is using Illumina's Dragon software on AWS, and there are a large number of customers using this technology today and the architecture shown, where they're using the AWS batch environment that I described earlier to elastically expand and contract the compute resources needed. They're also using Spot, which is our cost-effective mechanism for using spare cycles on AWS, which is up to 10 times less expensive than on-demand resources on AWS. And an emerging area that's extremely exciting is the area of cryo-electron microscopy. And all of the characteristics of this new research area are similar to genomics, except that the imaging allows them to do very accurate molecular structures, to mimic and to see and mimic molecular motions, and then feed those into simulations that they do to be able to design drugs, look at the effects of different drug candidates on disease and upon biological systems. The infrastructure used for this type is very similar. Typically, a user will set up an FSX for Lustre file system for the high bandwidth input and output, but they also use local NVMe storage. They use a device, they might choose an instance that has local SSDs on the compute nodes, using parallel cluster rather than batch to automatically set up and create shared drives in a shared environment. Other areas and applications that might be familiar to you are using codes like LAMMPS, which is a molecular dynamics algorithm and a molecular dynamics simulation code. And we've recently done simulations up to 50 to 60,000 physical cores using LAMMPS, and seen that using our elastic fabric adapter networks and MPI-based applications, we can see almost linear scaling up to 50,000 cores. And that's shown here. 48,000 physical core system, simulation of 27 billion atoms was recently done for a customer engagement. And was basically linear scaling out to 500 nodes. CP2K, a materials science application, also showed good scaling, not quite as good as LAMMPS, but very good scaling up to 4 compute nodes, which is actually fairly common for CP2K. It doesn't quite scale as well typically as a code like LAMMPS. Maxar, I mentioned earlier, is a commercial company that is doing production weather forecasts every day that they use to help farmers and other of their customers make decisions on whether to plant crops or give insurance companies information on whether and how much they should provide insurance for areas that might have climate change going on or weather events going on. So I wanted to show you a weather simulation using WRF. And in this case, we took the WRF code used for production weather forecasting, and we ran the simulation on a range of compute instances, Intel x86 architectures, AMD-based Rome instances, and our new Amazon Graviton 2 ARM-based processors. And we saw good scaling on all of these different architectures using elastic fabric adapter. And where this really becomes important is that the cost or price of these different types of solutions is quite different. And so the user can make a choice of whether they want the best performance or the best price performance. And then I talked about Formula One earlier. That's one of our lighthouse customers that's been working with us for several years. And again, one of the exciting areas is that they are looking at how to combine both AI and ML machine learning algorithms with their CFD simulations in order to get dramatic improvements on the turbulent models that they're using. Codes like StarCCM, Fluent, OpenFOAM all scale extremely well on AWS out to anywhere from 5 to 10,000 physical cores using our elastic fabric adapter. And finally, as you know, we come to the end of the presentation, I wanted to make sure that when you get the PDFs for this, that you can go off and read about some of the success stories that we have. So I provided a summary of some of the recent products that we made available and some of the success stories we have with customers and some of the benchmarking results that are available. And you should be able to access these once you have the PDF from this presentation. I always like to end with this slide because you know, I've been in high performance computing for a long time, and I thought that I really knew all there was to know about approaching scientific problems with high performance computing. And what I've learned over the last 2 or 3 years is that I was wrong. I learned to rethink the way that scientists could approach these problems and to begin to reinvent themselves and the way that they approach these problems in order to achieve even better and more performant results from their science. It's not to say that cloud solves every problem better, but it is to say that you certainly have a lot more agility and flexibility, and you shouldn't have to compromise in order to get that flexibility. And hopefully I've shown you today that AWS does not compromise results. Thank you.
Great, thanks, thanks, Barry. That was excellent, really enlightening discussion. I guess let's open the floor to questions now. People can just unmute themselves and ask if they have any questions. Yes, Vivek.
Yeah, my question is the following. Is cloud computation cheaper than, let's say, fixed resources computing? Or is it that on a certain time scale, this is cheaper? Or is it just that it enables you to have more resources? Of course, it's probably a mixture of all of these. But as far as cost is concerned.
Yeah, I mean, the answer is yes. It is both cheaper and more expensive. It can be cheaper, and it really gives you the choice of how much you need to pay in order to get a result. There are very inexpensive and efficient ways to use the cloud. And many of our customers are very cost conscious. They want to be very efficient. If you have a workload that never changes, and if you have a workload that you know for 3 years or 4 years, you know how much work you're going to be doing, then buying a computer is a very efficient. You can keep that computer running 24 hours a day, 7 days a week at 90% utilization for 3 years, and you don't have any other requirements. On-premise systems are very cost effective if that is your use case. The question is, many people don't have that. They don't know how much their computing is going to fluctuate, or it's going to change over a year or 2 years. And they're taking a risk. They are spending, in some cases, more money because they are forced to make a commitment to a technology and stick with that technology for many years. That is a cost. There's a hidden cost there that now you aren't using the latest technology, you're using an older technology, and you're going to be running more slowly. So I think the answer is cloud can be much more expensive, but it can also be less expensive. And it can also provide you with more choice. You can experiment with new algorithms, new technologies every day.
Just one more question, if you allow me, Girish. Yeah. Are some of the big experiments thinking of moving to cloud, at least partially? Like, let's say, the Dune experiment in the US and let's say some of the experiments at the Large Hadron Collider at CERN.
Look, one of the most exciting things that I get to do is run, we have a class of problems at AWS we call million core simulations. And when we're working with a customer on a very large processor. It could be a million cores. It could be 1,000 GPUs. I mean, it really is very large scale, something that typically is not done. And since I have been here, we've run dozens of million core workloads with our customers. One is in the references that I just gave with Woodside Energy in Australia. And they did a press release. They were so excited when they were able to take a seismic workload and take one that took a month to run on their on-premise and run it in a few hours on 1 million cores. And, you know, they were just, you know, and that gets them to a solution faster. They can make a decision on whether to buy access to a reservoir because they've done the simulation and they make a decision faster than their competitors. We have a similar result that's a drug discovery result that will be public soon. I can't say the company and the university that we worked on with, but basically 1 million core and greater, looking at drug discovery and looking at screening billions of drug candidates in a few hours. And it's really looking at a whole new paradigm there for drug discovery. And we have many, many more of those examples. They're the most fun is working on those types of projects with customers, whether they be commercial companies or universities.
Thank you.
Great, thank you. Are there any other questions, comments?
There's one question, Grace, from YouTube, from Malakre.
Mm-hmm.
The variations of internet connectivity in India, how would cloud computing be of real assistance? What guarantees for society of the data, security of the data, I'm sorry, and computations in terms of national emergencies?
Yeah. We at AWS take security extremely seriously. And you know, you can see that by the range of by many different ways. One is the types of companies that work on AWS. We have many companies who are competitors with each other, all working on AWS, and we protect all of their data. We do not share data. We do not share our data even with Amazon. AWS is a separate entity within Amazon. And Amazon is a customer of ours. It's not even what Amazon do. Amazon might do simulation and modeling on AWS, and we treat them as a completely separate customer and do not share data with them. In the same sense, we do not share data among customers. In terms of, we do work with many countries that have policies around keeping data in country, you know, and Germany, for instance, we have a data center in Germany because, you know, they have certain requirements for medical and other types of information that the data cannot leave the country. So what we do is we work with every region and we work with every country. We work with every customer, and we make sure their data is secure, that it's not shared with anyone. And we put the full power of AWS security. We have more people and we have tools that are continuously monitoring the security of every one of our data centers. We're able to take those tools and we use the same tools to protect from cyber, any type of cyber intrusion, the same tools that we use in our government clouds and in our public clouds and in our largest regions where we have, you know, very large infrastructures, and we use the same tools in our smaller regions. So we're actually able to leverage all of that security technology and make sure that our users' data is safe and secure. And we take that extremely seriously. Is that I just want to make sure I'm answering the right question here and that I understood it properly.
Well, Mary, this question was from YouTube, where the participant types out, but I'm sure I'll see if your answer satisfies his question. Yeah, maybe Girish, right. Take one question. There's also on Zoom chat box.
Yeah, actually, before we get to that, I wanted to take the question that Vivek Datar asked a bit further and Barry, get a bit more out of you on this issue of cost management. So as a publicly supported organization, we need to justify a given technological solution and its cost, right? But we appreciate that our workloads keep fluctuating, scientific opportunities come and go, and it's very difficult to predict what precise problem we would be working on in the next 3 to 5 years. We also appreciate the intangible advantages of cloud, like agility and flexibility and so forth. So I wanted to hear more of your thoughts on what is your way of thinking rationally on matters of cost comparison when it comes to strategic planning for computing establishment in organization like ours.
That's one where we're going to have to sit down together. So I want to. I sat down with a national lab in the U.S. just a couple of days ago and talking about a very similar situation, and they want to be experimenting on the cloud. They know they need some on-premise resources. They know they have some highly fluctuating workloads, and had this exact same discussion. I have ideas, for instance, but I need to vet them with institutions like TIFR. Those ideas include, can we give you a cost estimate and show you a structure of costs, and then let you think, okay, should I set aside 20% of my budget for cloud and agile environments for now and experiment with that for a year or two, and so it becomes a standard portion of your procurement where you're thinking in terms of this much is for agility and this much is what I typically do on premise. That's one approach. And we can work on that. And then over time, as you learn confidence, you learn what workloads, you get better at predicting, and you can then say, okay, maybe it's 30% of my budget that's agile and flexible. And you begin to tune in on exactly what that, it's going to take experimentation just because there's so many choices in the cloud. Like I said, you can choose to get compute resources when you need them right away, or you can have the researchers choose to only get spare resources on AWS at a very cost effective. So I think we should sit down and do a little modeling and think about what types of models could work. And then you have to work with your government and funding agencies to see if they're willing to have this much, for CapEx, capital expense, and a portion for agile compute. And then we start building procurement mechanisms and RFPs and RFQs that can map to that type of purchase.
I see. Okay, great. That's very helpful. But again, just sorry to belabor this point, but this is a sort of a core topic of discussion internally for us. But what sort of behaviors are you seeing from your academic customers? Are they have they stopped thinking of building new data centers and just jumped on cloud? Are they doing a cloud plus on-premise synergy type deal, or are they just ignoring cloud for development purposes and only doing cloud for specific project-based computing?
I will say we're seeing more commercial companies decide to make an economic decision to only use cloud. Public sector is a little slower, and I think it's for the very reasons that you're specifying. Because in public sector, it has to map to the funding model, and you have dozens or hundreds or thousands of researchers to make sure you satisfy. And so I think in the public sector, we've seen a little more hesitancy to go all in on cloud. But I don't think there's anything intrinsically different. I just think some companies choose both. They choose to have on-premise and cloud because that's what works best for the type of data and the type of problems they're solving. And companies that go all in on cloud, that's because that works best. For instance, many new companies, startups, tend to not want to build a data center. That's just, they don't want to even start developing those costs. And so we're seeing a little more in the new companies, small companies that want to go all in on cloud. I think the same is true of small universities and small public entities, research institutes. If they're smaller and they have a smaller community, then they may not want to make the investment of building a computer room. And then it becomes a simpler choice. It's a harder choice if you already have that infrastructure, you already have a data center, you already have a computer room. And I think those are the customers that we're going to have to work with over time to find the right match.
Great, thank you. Sorry, if I can just take my privilege and ask one small bit before we end, Satya, if that's okay. I was this should be very brief, but a last piece of the economics puzzle is that it's not just AWS. In India, at least, there are these big three cloud players, Oracle, Azure, and AWS. Could you comment a bit on the relation between these clouds from a customer perspective? Because what happens is sometimes an RFP bid is won by Amazon, next time it can be won by Azure, in which case there are issues of moving data from one to another, and so on. I was just curious to hear your thoughts briefly. Thanks.
Well, I mean, I can't speak to our competitors, but I can speak to the high performance computing value and teams that we're building at AWS. So I don't know what our competitors are doing. I do know what we're doing. So, since I came here 2.5 years ago, I built up a team by a factor of 10 that has all of the expertise in the workflows and workload areas that I've described. We have computational fluid dynamics experts. We have weather modeling experts. We have people who are experienced in basic physics and chemistry. We have healthcare and life sciences experts, scientists, basically PhDs like myself, or people who've been working in the industry in drug design and drug discovery and genomics, data scientists who've been doing machine learning and training. On my teams, I have all of those. And the reason that we have those teams is because you can't just sell the infrastructure. We've done all this great work of building up products and services, of building an EFA network and a Lustre file system. But that alone is not sufficient to help customers journey to the cloud. It's a journey. You're on a journey. What is that, where that journey ends? It might end up at 20% in the cloud, might end up at 100% in the cloud. But you need a trusted advisor to help you on that journey. I can't speak to our competitors, but I can say that the teams that I've built here and that we've built here are as good as any team I built at Cray or IBM or any of those companies that I was at. And the teams I manage are as brilliant or better. They're fantastic, and they're able to help customers on that journey. And that's the value that we're trying to provide, whether it's in India or in the US or in Japan or Singapore. We are trying to provide that expertise on that journey. It's up to you to determine whether we provide that as good as our competitors or better than our competitors.
Great, thanks. That was excellent. So I guess we have had
I hope you are not kind of summarizing, but there's this question by Alak in the YouTube. It had actually two parts. So one part was answered by Barry, but the first part where he also talked about the internet connectivity issue in India, how would it affect the cloud computing paradigm? So that question was not answered. So
Oh, I'm sorry. The cloud computing, once, the simulation in the cloud is going to be all on the AWS backbone. Now, moving data around, it depends on, as you say, on the edge, on the interconnectivity to the actual. We built technologies like can have the computation happening in the cloud where there is good connectivity and a visualization straight back to their laptop, and have that visualization only. So they're not having to worry about the latency of anything except the streaming of bits for the visual part of the problem. The rendering all happens in the cloud. And so all of that complex rendering is happening. All of the complex simulation is happening. And then the scientists are utilization on this to try to help, and engineers in India are using that technology to share data with engineers in Germany today. So we have that type of technology. Again, between our data centers, we have very fast connectivity. We can move data between data centers very quickly. So I'm not worried about those two aspects. I can't speak to the actual end connection to the scientist and how that is. But like I said, we build tools that try to make they're not actually sending large amounts of data.
Great, thank you. I guess we should try to wrap up now. Is there any last question or comment?
Maybe, Girish, if I can ask.
Sure. Satya, go ahead.
This probably is a name question, or maybe you have implicitly mentioned the answer. But during the days of the LHC experiments, early or mid 80s, and the question of what is the projected computing power that is required for data acquisition or computation, the machines that existed were, of course, very rudimentary CPUs, boxes at that time. And but one knows what their computing power is, and based on that, one could extrapolate and say that what kind of machines probably will exist at the time when the machine gets turned on in let us say late 2000s. And so this comparison may not be up, but the question now is that when somebody wants to make a decision whether to do a kind of difference between on-premise versus cloud-based solution, is there some data or the procedure or something where somebody can kind of compare them, compute them, maybe simulate them and say, okay, I can see that the cloud-based computing is going to give an edge over, buying the hardware on campus and so on. Are there some help or information or database or whatever you call, which will help the end user instead of listening only to you, but the end user, a little bit knowledgeable, and the end user can actually make a more informed call that which one of them will be a better solution for given a problem?
This is the same problem. I mean, the same situation that we've had for a long time with even at Cray when I was there. I mean, these are very similar situations, which is how is the end user going to predict? I think there's two answers to this. One is the base technologies we're using. If you're using an x86 CPU or an NVIDIA GPU, you're going to get the same roadmap presentation from NVIDIA or Intel or AMD that we get. Well, maybe similar, a very similar roadmap. And your projection of those technologies is going to be very similar to our projection. And we're going to stay on the technology curve with those partners. So, there's no new information you're going to get from us necessarily that you're not going to get from Intel. And then we can talk about why we make certain choices about processors, but we tend to choose general purpose processors much the same way any of our competitors do. So I don't think there's much difference there. For special purpose devices, that's a different story. I mean, and every technology is evolving very quickly. Our inference and training technologies are evolving very quickly. In that case, we need to sit down with you and do an NDA-based presentation and say, here's what the current technology is, and here are some of the things going into the next version of that technology. That's not public information. That's a non-disclosure agreement and a discussion of the roadmap. But I do think this gets to a problem that is the way we think about on-premise is we put the prediction on the user. The user has to make a prediction of this because they're having to make a capital acquisition. They're having to place a bet on a technology. When you work with AWS, you don't have to place a bet on a technology. You can place a bet on your application, and the technologies AWS places bets on and takes risks on. And you always have access to the latest and the best. And I think that for some people who love technology, that's a hard thing to give up. I love technology. I want to make the decision of what technology I get. But many scientists, that's not the key question they have. The key question they have is how do I design a better drug? Or how do I make a better car or a better airplane? And if they know they're always going to have access to the best technology, then I think it takes a worry away from them. So maybe that's a way of not answering your question fully, but I think that's all I can say, today.
Can I just add a small comment?
Yes, please, Kajari.
Yeah. So the point is, Satya, what you said, okay, by say, for example, late 90s, people started realizing the amount of data volume LHC will produce, and that's how the grid technology was evolved as a natural evolution from the WWW. But the point is, during last decade, LHC was rather the strategy worldwide was such that LHC's lifetime was increased by 2 more decades, you can say. When it was initially planned, it was not supposed to run till, say, for example, 2035 or so. But now it is so. And the computing needs will be much more. But at the same time, what has been realized is that CPUs are not able to provide as much acceleration as being provided by GPU because of the structure of the chip, etc., etc. So sometimes as a scientist, we have to keep track of the technological progress, and things do come, and that turn over the whole attitude towards attacking the problem or the strategy. So for example, CMS and LHC experiments mostly, now a good fraction of it is running on GPU systems, which was not really planned to be the case. And what was started the efforts for GPU, say, for example, 5 years back, things have developed so much. Now we are going to employ those GPU-based software in a year's time. It was meant for high luminosity LHC, but now it is going to be employed for the run 3 of LHC. So you cannot really project so much. You can sort of estimate that how much power I will need, but then what type of technology it will be, that depends on the development. Sometimes we end user may not be able to guess it so much. But I know that at CERN, the technology, Intel, etc., they do provide their internal technologies for the CERN scientists to run their codes on, to really check, to make a comparison. And there are softwares which really rather, you can say, platforms where you can compare AMD versus Intel, etc., that we do on regular basis. Like for our recent enhancement of resources, our engineers did so, AMD, Intel, etc. And you put it up on the open platform, and then you see how things are, etc.
Yeah,
and it was
in cloud
about 6-7 years. I'm sorry, 6-7 years back, that the CPU-based resources what LHC experiments were planning to have will not be enough. So there was a panic. So in fact, Fermilab scientists went to AWS and they did run. They went to, that was the first time that CMS experiment went to cloud resources. And then it was felt that yes, things are, one can elastically increase the computing power. And based on that, even Bridge, etc., tried to do it on Microsoft. So anyway, that's what I wanted
Yeah,
to add.
no, that's exactly correct. And I think what AWS wants to do for high performance computing is provide that environment that allows the researchers to test new technologies as they come out, and then quickly and agilely move to those technologies if they have benefit. I mean, that's why we're developing an inference roadmap and a training roadmap. It isn't because GPUs are not good for that. It's because those offer potential gains as well that are yet to be determined. And again, we're not asking people to commit to that. We're asking them to experiment and to try out those technologies. And if they find them valuable, move to them. And I think cloud offers that. If users are flexible with how their algorithms work.
Yeah, of course, it needs a lot of effort initially from the user end, that changing the code, going much more towards vectorization.
Although we are seeing one of the exciting trends in HPC is the continuing containerization of applications, and more scientists are working with very agile programming models and programming environments, whether that's things like Red Hat OpenShift or Kubernetes or various containerization methods. And the more they work with those, then the more agile they can be in cloud environments. And those don't disqualify, and they can still use these in on-premise systems as well.
Great, thank you. That was a very fruitful discussion. Thanks, Kajari, also for that comment. So I guess let's close the colloquium now. Barry, I want to thank you for an excellent presentation. It was very enlightening. It touched upon several of the critical issues for us. And thanks also for the Q&A. I also want to thank the Indian AWS team, Juhi Mistry, Irshad Chauhan, and Sudeep Roy, who are on the call for facilitating this meeting. I think we look forward to having interactions with AWS to understand if these solutions can indeed help us do our science better. But otherwise, I guess I'll say thank you and good night.
Thank you very much. Good night.
Bye.
Bye.
Bye. Thank you, Girish. Bye-bye.
Bye.
Bye.
Very, thanks very much.